about today are power functions. This will lead us into next time, which deals with polynomial functions. So, a power function is a function in the form f of x equals k times x to the p. K and p are both constants. So basically what you have here, a power function is any sort of function where you're taking some power to the variable. You're taking the variable to some power. All right, so the first couple examples is just asking us whether each of the following are power functions. What we are also going to do is rewrite some of these so that they are in the form k times x to the p, okay? Let's look at the first one. So what we need to be thinking about is, can I somehow rewrite this so that my variable is taken to a power? Amber, you're shaking your head yes. How can we rewrite this so that our variable is taken to some power? Close. How do we rewrite the cube root as an exponent? It's not to the third. Gabby? It's to the 1/3, okay? So we can rewrite this function as f of x equals 13 times x to the 1/3. Because I can rewrite it so that my x is taken to some power, this is a power function. What about the second one? What do you guys think? Can I rewrite that somehow so that it's in this form? Not really, because we just want the variable to the power. We have to be able to write it in this form where you have just a constant times x to the p, or to a power. Can I somehow rewrite that in this form?
You can't distribute it. It's like one. Is the answer no?
The answer is no. If you multiplied all this out, you would have several terms here. This is a polynomial function, which is taking several power functions and putting them together, okay? So this is not a power function. I cannot rewrite this expression in this form. If you multiply that out, this would have several terms. What about the next one? Can I somehow rewrite this in the form y equals k times x to the p? What do you see here that we can maybe work with? What's a square root, guys?
Oh, you could square the whole function, so then it would just be 25 over x cubed. Would you switch the variable and solve for y? No. Okay.
Think about what we did on the first one. How can you rewrite a cube root? How can you rewrite a square root? Ty? Yes, you're on the right track. So you can rewrite that radical as 25 over x to the third all to the 1/2 power. And then we can apply that power of 1/2. Well, it's 25 to the 1/2 power. 5. And then x to the third to the 1/2. Okay, exponent rules here. Guys, what do you do when you take a power to a power? Multiply. So this would be over x to the 3/2. And then we can move that denominator up to the numerator. So we can rewrite this as 5 times x to the negative 3/2. That is in that form, k times x to the p. You have that value of k, you have some power, okay? So this is a power function. So don't think you're just going to be given a function straightforward that looks like that, y equals k to the xp. You're going to have to probably do some manipulation there. All right. Okay. What we really are going to spend a little bit of time on is looking at the graphs of different types of power functions based on that value of p. So based on what the actual power of the variable is. So we'll do the first two together, and then I'm going to let you guys kind of play around with your calculators and look at what these different types of graphs look like on your own. Okay, so we have two special cases when your power is 0 and then when your power is 1. So if we have y equals x to the 0, what is anything to the power of 0? 1. So this is really y equals 1. What does that graph look like? What kind of line? A horizontal line, exactly. What did you say? Okay. If we have our value of p equaling 1, meaning that your exponent or your power is 1, what does this graph look like? Y equals x to the first. Come on, people. You were in middle school, right? You somehow got here. What does the graph of y equals x look like? It's a linear function. What's the y-intercept? The y-intercept is 0. What's the slope? Okay, come on now. Don't make this too hard, okay? Oh, by the way, I should have mentioned that your coefficient k in all of these is 1, okay? What we're really focused on is how changing your power or that value of p affects the graph. Okay, so what I want you to do is this. So you are going to look at changing up that value of p. So you can see in the next section that you are going to look at positive integer powers, both odd and even. You are going to look at what happens to the graph when you have negative integer powers, again, both odd and even. And then you are going to look at what happens when you have positive fractional powers, meaning your power is a fraction, again, both even and odd. So here's what I suggest you do. I guess I'll do the first one with you so you have a clear idea. So take your calculator and just look at this first one. We're looking at positive integer powers, in this case, odd integer powers. Go to your graphing, just type in, I mean, you don't even really need all three. I would even just look at the first two. So x to the third is your y1, and then x to the fifth is your y2. You might want to change the type of line so you can really distinguish between the two. And then graph both of them on the same grid. If you feel like you need to, you could zoom in to get a closer look. Just kind of whatever you think you need to do to see what these graphs are doing. But what you're going to find is that each of these graphs have the same kind of general like form, but increasing that number changes it a little bit. Okay, so what I want you guys to do on your papers, for example, for this one, just kind of sketch in the graphs that you're seeing. It doesn't have to be like super accurate or anything. Your book calls this chair shaped. If you kind of think about like a person sitting in a chair, that apparently is a mermaid. They have two arms and a tail. Huh? What?
It still like arms. It looks like a floating head, two legs, and
Okay. So this is like a chair-shaped graph, and you might want to make a note about the fact that x to the fifth is steeper than x to the third. What I mean by that is if you look at my darker one, it is like skinnier, okay? It grows to infinity a lot quicker. So just make some general notes about the shape, and then if changing that number bigger, smaller changes at all. Does that kind of make sense?
yes.
Okay, so I'm going to give you a little bit of time to work through that. Again, general kind of sketch of the graphs, any special thing that you see. Okay, go.